Our next problem is for what values of p that this series converges. The series is 1 divided by n to the power p, right? Now here also we are going to apply the integral test. So for that one we need a certain function. Now since the values of an are equal to 1 divided by n to the power p, we choose our fx as 1 divided by x to the power p, right? And the domain of the function should definitely be defined like this, right? Because that is the one which is mentioned in the integral test, right? And then also I should say something about this domain. Now it is not always a must to start at 1, okay? It can even start at a integer greater than 1. Say if we can even start the domain at 10, right? But then if the conditions are satisfied, we are dealing with this integral, okay? And so we should from this integral it discuss the convergence of this series, right? So even for the series also you will get you will start it from the same point that this integral is also starting, right? But you cannot have it for the numbers which are less than 1, right? You can start the domain from the numbers which are greater than 1. I mean integers which are greater than 1, because for the series we are going to use integers, but not for the number integers less than 1, right? So if we are starting at a number which is different to 1 for the integral, then the corresponding series will also should start with the same number and not 1, right? Okay, so now anyway, since our series is given in a way that it starts at 1, we should also use the domain for the function starting from 1, right? And then now if p is greater than 0, right? That means if p is a positive number, we will discuss later what will happen if the value of the p is equal to 0 and what if it is a negative number, right? But just for the time being, let's consider the case where p is greater than 0, right? Then you can see that the function satisfies these three properties which are mentioned in the integral test: continuity, positivity, and the decreasing nature. And for the decreasing nature, you can use the same calculation that we did before to prove that this function will also decreases, right? So if we have two positive numbers, because we are choosing the numbers from this domain, then it says that x to the power p is greater than or equal to y to the power p. So y to the 1 over y to the power p will be less than or equal to 1 over x to the power p. That means fy is less than or equal to fx. So we have proved that if x is less than or equal to y, then fy is less than or equal to x. That means fx is a decreasing function. So we have a function that satisfies all the requirements for the integral test. Then we just have to consider the convergence of the improper integral 1 over x to the power p. And we specifically did this one when we were dealing with improper integrals, and we saw that this integral converges if p greater than 1 and it diverged when p is less than or equal to 1. So from the integral, now this comes from the previous week's it is not from the previous week, it's actually from the section on improper integrals, right? So anyway, from that section we know that we have the convergence for this improper integral when p is greater than 1 and it diverges when p is less than or equal to 1. So from the integral test we can say that the series will also converges when p greater than 1 and it diverges when p less than or equal to 1, right? So from the integral test we have that the series converges when this happens and it diverges when this happens. So this is from the integral test, and this result that goes with the integral comes from the knowledge that we had in the section of improper integrals. And there's one more thing that we need to do, right? Now all these things were mentioned for the case where p is greater than 0, because then only we can write down this inequality, right? So basically this will be true when we have this condition, right? So how about the other case? Now that means what if p is equal to 0, what will happen? So when p is equal to 0, that means our sigma notation will be equal to sigma n equals 1 to infinity 1 over n to the power 0, right? So that means it will be equal to sigma n equals 1 1, right? Now this is also another important thing that a considerable number of students make mistakes, right? So now normally you tend to write the answer for this series as 1, which is not correct. The reason is, now when you have a series like this, it can be represented like this also, right? So here it says our series, now if we expand the terms in our series, then it will be something like this, okay? That goes up to n and it goes forever, right? So if we have a series with a constant like this, okay, that means our an sequence, okay, our an sequence is the constant sequence 1, okay? So our an sequence will be a constant sequence which has got 1 in each and every position, right? So that means when you write down the expanded terms properly, it will be something like this, right? It's like you are adding 1 forever, right? So it will eventually go to infinity, right? So basically this series will diverge, okay? It is not equal to a constant number. This is very important, okay? Because most of the times students make this mistake at the first glance, right? So be careful whenever you have a series with a constant like this. It can even be a fraction like this, right? It's like you are adding this number for infinite terms, and eventually you will get infinity no matter how small this number is, right? So be careful with this, like with the correct interpretation of this symbol, okay? Because now normally if you have integrals or derivatives, when you have a constant inside the integral or a derivative, you can take the constant out from that integral, right? So there won't be a big change for the integral, but here it says a different idea, okay? It's like we are adding this number inside infinite times, right? So the best way that you can recognize, or like to interpret this sigma notation, a very good way is to visualize it as a sequence of an terms. So here an was equal to the constant sequence of ones, and then sigma notation says that you have to add up all the terms in this given sequence, which is in this case we are adding 1 infinite times. So what we have is, when p is equal to 0, the series diverged, right? So without any tests or any outside source, we can directly see that the series diverges, okay? Right, like if you prefer, you can even write down the partial sum sequence, and in this case the addition of first n terms will be equal to n, right? So basically the general term of the partial sum sequence will be equal to n, right? For example, S5 represents the addition of the first 5 terms, that means 5, because each term will be equal to 1, right? So accordingly the Sn sequence will be equal to the sequence of n, and that sequence will diverge. Therefore the series will diverge, and we are left with only one more condition. Now we have dealt with the situation where p is greater than 0, and right now we discussed the case where p is equal to 0, and finally we need to see what will happen if p is less than 0. That means what will happen if p is a positive number, a negative number, right? So in that case, what we can do is, if we consider this series and see if this is the an term, when p is a negative number, okay, so for example, if p is like negative 10, an, the sequence of an can be written as n to the power negative 10, which is equal to, now these are curly brackets, okay, that is equal to n to the power 10, right? So whenever you have a negative number as the value of p, you will end up with a situation like this. So eventually we can say that the limit of an is equal to infinity. And in the previous week we discussed a thing called divergence test, right? Which says if the limit of an is not equal to 0, then the series will diverge, right? Now if you don't remember this one, please have a look at the previous videos, right? So now here in this case you can clearly see that the sequence of, now this is not the partial sum sequence, okay, we are considering the sequence of an terms, okay. So here we can see that the sequence of an terms will not, the limit of this sequence is not equal to 0, right? So from the divergence test we can say that the series diverges. Now as a summary we can say that the series 1 divided by n to the power p, where n starts from 1 to 1 and goes up to infinity, and this series will converge when p is greater than 1, and it diverges when p is less than or equal to 1, and even this p value can be a negative term, right? And you must remember this result, okay? You must, it's like very, very important that you remember this result, okay? And there's one last thing that I want to mention about this result, or rather the integral test. Now say if we have this series n to the power, let's take it as 2, okay? So from this result itself you can say that the series converges. That means it basically has a value when you add up all these terms. That means when you add these terms, 1 squared, 2 squared, 3 squared, likewise when you add up all these terms, it will have a finite value, right? And now let's say if we don't apply, like instead of using this result, if we directly use the integral test, then the function that we are going to consider will be this one, right? And you can see that by using the improper integral techniques, you can see that the given this integral converges to 1, okay? By evaluating this, now here you should have t, and you can see that this integral, the answer for this limit is equal to 1. That means this integral is equal to 1, right? So from the integral test we can say that since this converges, this series will also converge. But the thing is, now these two answers need not to be the same, right? Just because this integral is equal to 1, that does not say that the answer for the series should also be equal to 1. There's no such relationship like that, right? The only thing this says is, if this has a finite value, then this will also has a finite value, but it does not say that these finite values should be equal, right? Actually this value should be equal to pi squared over 6, and we can do like we can obtain this result from some numeric techniques, but we are not, like at the moment we are not going to discuss it here, right? So keep in mind that these two finite values need not to be equal all the time,